Okay, so as promised, we're going to change gears quite abruptly at the beginning of this lecture, and hopefully by the end of it, we'll make contact with what we did in the last two lectures. And along the way, I might mention some of the things that we discussed in yesterday's discussion session. Okay, so some physics background first. So the motivation, our motivation for coming to study the kinds of things that we've been discussing in the cluster algebras came through the study of scattering amplitudes. And the fact that these things are related to Wilson loops. There's a duality between scattering amplitudes and Wilson loops in a particular theory, in planar n equals 4 super Yang-Mills theory. So I'm just going to go through, give a very brief introduction of the kind of some of the basic physics quantities, which is going to justify, hopefully, what our kinematic data is and why we are interested in Grassmannians, and then why we might be interested in cluster algebras in the first place. So imagine you have a scattering process, and we're going to be in a planar theory, and the net effect of that, for the purposes of this talk, is simply that I'm going to have an ordering on my external legs for the scattering process. Okay, so then the particles come in, they've got momenta, P1, P2, all the way around to Pn. And I'm in a theory where the particles are massless. So these particles, they obey an on-shell condition which just says that the square of each momentum is 0. Okay, so the momentum is a 4-component vector, Lorentzian signature, and these are light-like. They lie on a null cone because I have massless particles. Okay, so because of that, it can be, or the second, there's one condition, they each satisfy this condition separately, and there's a second condition that relates all of them, which is that we have momentum conservation of our process, so all of the momenta add up to 0. So this picture, therefore, in order to solve this second condition, it's convenient to introduce dual variables. So I'm going to write each momentum as the difference of two auxiliary variables that I'll call x. Okay, so you imagine there's some position space somewhere that's somehow a recoding of this momentum space, and I'm simply going to write each momentum in the cyclic ordering as the difference of two new variables that we introduce, xi plus 1. And then in this x space, this kinematics for the scattering gets related to a sort of piecewise linear contour that does something like this, and it goes around and it closes because I telescope the sum and solve the momentum conservation. Okay, so then we are left with the corners on this space being marked by these xi variables, and the edges in this space are the original momenta that we started with, P1, P2, etc., as you go around the curve. To solve this on-shell condition for each particle, it's convenient, instead of writing these things as 4-component vectors, to package them into a 2x2 matrix whose determinant replaces this square of the vector. Okay, so I'm going to introduce a matrix version. I'm going to replace my 4-component pi mu with a 2x2 matrix pi alpha dot. There's a 2x2 matrix. This thing is going to tell me that the determinant of this 2x2 matrix version of P is going to vanish. And therefore, I can write each 2x2 matrix as an outer product. These two objects that I'll call lambda and lambda tilde. Okay, so that's just a way to solve this condition, is to introduce these lambda variables, and then I'm guaranteed I'm solving this on-shell condition. Okay, Now, it's convenient, actually, to introduce a third space. So the third space is going to be projective space, which will be over here in this cartoon, the three-dimensional projective space. And the way we're going to introduce it is that if I have a point x in this dual space here, so one of these x's that lives in R4, R4, I'm going to map it to a line in this projective space. And I'm going to do it by writing down the following equation. Take the 2 by 2 matrix X and contract it with the two-component lambda I've got here. Okay, so imagine I've got a lambda. I define mu via X, or if you like, what I fix X, and I look for the set of mu and lambda, which solves this linear equation. Okay, now the pair mu lambda, or lambda mu, we're going to call that, I called it W. So W is the pair lambda and mu. And obviously, I don't care about rescaling lambda and mu here. That's not going to change the, it's obviously homogeneous, this equation, in lambda and mu. So I'm going to mod out by the scaling in lambda and mu. And then I'm going to study the space of all solutions lambda and mu, W, that live in this P3 space. So this is this line. So I can mark the line with the original point that I started with. Okay, so you can map points in space-time, or this dual X space-time, into projective space through solving this linear relation. And now, suppose we have two. Suppose we have the lines, x1 and x2, the lines for x1 and x2. Suppose they intersect in P3. Okay, so we have our P3, two lines, they intersect at a point, one for x1, another one for x2. Okay, so suppose they intersect, then it's clear that there will be a point in P3, W, lambda mu, that's the intersection point. So it's on both lines. So I have mu equals x1 lambda, and mu equals x2 lambda. And so you can conclude that if I take the difference, 0, x1 minus x2 and lambda, I conclude that the 2 by 2 matrix X has a null eigenvector, so it must have vanishing determinant. Okay, so det 1 minus x2 is 0. And then we said before, what does that mean? That means that x1 minus x2 has null, is vanishing in, its square is vanishing in the Lorentzian space-time. So x1 and x2 are like separated. They lie on a null cone, a null ray. In R4. Okay. So, oh yeah, sorry, there's a question? Okay, very good. Yeah, I skipped that, so let me be totally explicit. So, introduce the following four matrices. These are 2 by 2 matrices. The identity matrix, and then, okay, first Pauli matrix 0, 1, 1, 0, second Pauli matrix 0, minus I, 0, and the third one 1, 0, 0, minus 1. Okay, there's a reason I'm writing this down. It's to do with solving the a representation of the Dirac algebra in 4 dimensions. At least this is now completely explicit. This is how I convert, right? I put my 4 components. P1 is P1 times the identity plus P2 times this, P3 times this, P4 times this, and now I have my 2 by 2 matrix. Okay, right, so we conclude that this null geometry that we've got that's related to our scattering process is nicely described by intersecting lines in P3. Okay, and you can run this back the other way, let me not do it, but you can show that if x1 and x2 are like separated, then the corresponding lines in P3 must intersect. Okay, so then we've got a third thing that we could add onto the cartoon that we drew over there. We can rewrite this thing as lying inside P3 as a sequence of intersecting lines as I go around. And each one intersects the next one at some point. So that geometry there is equivalent to this geometry here. To specify this geometry here, I just pick a bunch of points and then declare that the lines are the points, give them an ordering, and then declare that the relevant lines are the ones which connect the adjacent ones in the ordering. Okay, and hopefully that picture is reminiscent of pictures I was drawing in the last couple of lectures when we started talking about automorphisms and Grassmannians. Okay, so now we're at the Grassmannian because what do we have? So we have a set of data, Wi. They're 4 component objects if I write them out, but remember I'm modding out by scaling, so they live in P3. So I have a 4 by n matrix, which we can think of as describing a point in the Grassmannian GR4n. And I should mod out by column rescalings as well. Okay, so, sorry, a very important thing that I didn't say. 4 by n matrix does not describe a point in the Grassmannian GR4n, because I should tell you, it does, but there's an equivalence class. I can act on the left by an action of GL4, and that will describe for me the same plane, right, with these 4 n-component vectors. I just move them around through the action of GL4. It doesn't change the plane they live on. Why should I allow such a thing? So it turns out that this theory is very special. And while many of those symmetries in SL4 are kind of manifest from the beginning, only in planar n equals 4 super Yang-Mills does it happen that there's an additional scaling and extra conformal symmetry that you get. So 5 of the 15 generators in SL4 are slightly surprising. But it is a true fact that in this theory, given this duality, also this duality is slightly surprising, but given this duality between, I didn't say what object lives here, but I wrote it here. So there's another object in the theory that you can compute given this data that turns out to be equal to this object, the scattering amplitude. That's a very surprising fact, in fact. But it has the implication that all of this data should be invariant under the full SL4 that acts linearly on these 4 component objects. Yes, you can. But the only problem would be if I'm not conformal, there's an extra piece of data which says where is infinity in space-time. So I could, if you want, I can keep the SL4. That's completely fine. But then I need a special marked line in P3 which describes for me where is infinity in space-time. So it just means there's more data. If you had less symmetry, then you can mod out by less. Or if you put more data, then you can keep the full symmetry and still have the same number of degrees of freedom. Yes, so that's correct. So if I'm going to represent it in these terms, I do need this massless geometry here. Well, kinematically, you can, so all we're caring about is what's coming in on the outside in this picture. So in some sense, yes, I can, because all I have to do is, if I want massive on-shell external states, I can make a massive non-null momentum by adding 2 null momenta. And then all I have to do is double the number of particles, and I could describe it this way. Might not be the best way to describe it, but you could describe it this way. Now, then you might worry about, well, what about all the masses on the inside? So then I would have to include them as extra pieces of, like, there'd be additional pieces of data in the theory. The amplitude would depend on also the masses of all the particles that I have in the theory, and that would not appear in this kinematic space. I'd have to add that additionally. That's right, yeah. So we're working in the same model that Daniele was talking about in his lectures. So n equals 4 super Yang-Mills is a conformal field theory, and realistic theories are not conformally, well, realistic theories of particle scattering in our universe are not conformally invariant. And the n of SUN, yes, I took that to infinity, and that does a lot of stuff. But for here, basically what it did is it gave us this cyclic ordering. And then my incoming particles are confined to have, I can confine them to have a particular prescribed ordering as I go around. And then I restrict myself to planar Feynman diagrams if I'm computing this thing perturbatively in quantum field. Okay, all right. So I should mod out by, I said GL4, but let me mod out by SL4, and then I will remember that I have column rescalings for every column. Right. So the duality, so the scattering amplitude is meant to be equal to a Wilson loop on this funny light-like contour. It's meant to have this conformal symmetry, which it almost does. So there's a slight subtlety that is not relevant for this, but there are divergences in this object, but they have a universal structure, and so we can kind of factor them out. So they depend on 2 pairs of adjacent particles, or equivalently, they're localized at each corner in this picture. So I should worry about them, but having dealt with them, I can just factor them out. Then there's an additional finite piece, which actually doesn't quite transform invariantly under this symmetry, but has an anomalous transformation. I'm going to ignore that too. And then the thing that I'm actually interested in, that's left over, that describes all of the interesting kinematics of this scattering amplitude, all the interesting dynamics of the scattering amplitude, is indeed invariant under this SL4. So there's parts to strip off, but the main bulk of this thing really is a function on the Grassmannian. That's what I'm trying to say. So there are massless particles, and so it's inevitable that I will have infrared divergences when I start computing this. This is well known, and there are many techniques for dealing with this, and it happens also in the real world in QCD when you compute perturbatively. And there are standard techniques for cancelling the kind of, they're called infrared divergences from virtual corrections against real emission of very soft gluons from external states. And there are ways to deal with the infrared. So here I am just going to factor them off and ignore them for the rest of the talk. Okay. So this is the bit that is finite and dual conformally invariant. And this dual conformal symmetry just means this SL4. Okay. So let's look at one of these. Suppose we have n particles coming in. And now we start exploring the territory of how these things behave, what kinds of functions they can be on the Grassmannian. So the first thing to say is they come in some guide. There's various types. So I can package them all together in one thing, but there's a thing called, there's different types of helicity expansion. The particles can have left or right-handed polarization, let's say. So you can have this, and there are different ways that you can choose the polarizations. And this comes in by the name of MHV expansion. So the first term is called MHV, it's called maximally helicity violating. Then there's next to maximally helicity violating. And it's a finite expansion which terminates once n is chosen. Just a finite set of amplitudes rather than just one amplitude to study for a given number of particles. What else can we say about it? So there's another parameter which Daniele also introduced, which is not part of this story here, but it's to do with the interaction strength of the particles in the theory. So this function, it is a function of all the points in our P3, but it's also a function of this coupling parameter. And we're going to expand in this coupling parameter, treating it as a small parameter. And the things that we're really interested in this story are the coefficients of that expansion. So there are, even within this choice here, there are infinitely many coefficients in a small g expansion that we would like to study the properties of. And the kind of the structure that you find, so what you find, there are various different types of function that show up here. Typically, what you find as you start expanding in perturbation theory, you find logarithms and dilogarithms and higher weight polylogarithms and more complicated objects. And you can also have, so those functions obviously have branch cuts in lots of different places. So you have singularity structure that's interesting. You also have some kind of rational prefactors that can have an interesting pole structure. So we have poles and branch cuts. It's a very familiar story from perturbative quantum field theory. So let me just sort of schematically write that you might have some rational prefactors, and then for each rational prefactor, something that has no poles anymore, but has branch cuts. There's some way of expanding this object that at least for low n, has a form that looks like this. We have some rational functions with poles. And some integral transcendental functions with branch cuts. I don't claim this is a general property. I'm talking about what happens when you start looking for n equals 6, 7, 8, etc. Okay, so a lot of the story that I'm going to tell you is based on computations and then observing the analytic structure that comes out of these computations. Yes? Okay, very good. So there are Euclidean kinematics. So there are conditions on the low. Okay, so there's a certain region in kinematic space that you could call the Euclidean region, and that region has a boundary. And it's the sort of the first place. If you're starting there, there'll be some first locations where you can start to see branch cuts appearing on the edge of this Euclidean region, let's say. Okay, in the underlying variable. So here are the components of this matrix. There's some underlying variables. There's some special regions in that space of underlying variables. There's a special region in which way, if you start there, and then you imagine defining your function there by analytically continuing. You start there and you analytically continue elsewhere. You will discover that there are certain locations that you can see that have branch cuts. Okay? And then if you start analytically continuing around those branch cuts and you come back onto a different sheet, you'll suddenly find that there are branch cuts in places where there weren't before. Single-valuedness. So I guess you have in mind things like the correlation functions. If you have a 4-point correlation function, you can think of it as a function of a complex variable in Euclidean space, and then its branch cut structure is constrained by the fact that it should be single-valued as you move the points around in Euclidean space. As an analytic function of z and z bar, treating z and z bar as independent complex variables, what that really translates to is that the branch cuts in z are correlated with the branch cuts in z bar, such that if you force z bar to be the complex conjugate of z, you would find that the discontinuities cancel out as you move around in this space. What that means is there's a region in space which only admits branch cuts on its boundary. And this will be true here. So there are certain initial singularities that are permitted in the scattering amplitude. And so single-valuedness is a sort of is an example of that feature. And a way of thinking about it in terms of scattering amplitudes is to say, where can you have physical two-particle cuts? So if I were to draw this, I could have, as one of my first branch cuts, I could have something that happens when the sum of these momenta squared go to 0. Two-particle cut. But then once I've analytically continued round that, suddenly I find cuts all over the place. Yes. Yes, absolutely. I can briefly mention that in few. Yeah. Okay, so, all right, so the main story that I want to talk about is to do with these integrals with branch cuts. But there's a version of this story which also includes behavior about the poles in these rational terms, and indeed how they interact with the branch cuts that come with the corresponding functions up here. Okay, so, well, what functions? Let me just write here, what functions? So at low n, so here I have n equals 6 and 7 in mind. 6 and 7, why? It's really to do with the dimension of this space. This thing only has non-zero positive dimension if n is 6 or bigger. Okay, it doesn't mean there are 4 and 5 particle amplitudes in this theory, but they're fixed by this symmetry. I'm going to skip talking about them and come to, they don't live on the Grassmannian, they're already fixed, taken into account essentially by these factors. And then if I want to talk about more interesting dynamics, I have to go to at least n equals 6. Okay, so what you find is that these functions are iterated integrals of kind of polylogarithmic type. So they're kind of the simplest class of iterated integrals. The very simplest version of something that Francis was talking about earlier. And they have a weight. So they have weight 2L, depending on what L I got. L. I didn't write L because I didn't do the expansion in G, excuse me. So each of these functions is a sum in some expansion in this parameter. By convention, it's G squared. So G to the 2L Rni-L, and L stands for the loop order. Okay, so if I go up in loops, I get iterated integrals with weight 2L. Very roughly speaking, I have a 2L-fold integral to do for each given L. Now, what I would like to talk about is what kind of integral. And what is the integrand? Right, specifically. Right. Okay, so we're going to define a class of functions that has a given weight. And I'm going to define it through this equation. I'm going to say I've got functions that come with some weight, k, and I will take their total derivative, and they will demand recursively that they can be expanded over some basis of functions at weight k minus 1 times d log of some rational or later algebraic function of my underlying data, which will be the entries of this matrix. Okay, so here A, some set of possible A's. So A will be, in the case of n equals 6 and 7, a rational, or later in the case of n equals 8, algebraic function of the Wi. We call each of them, some jargon, these things are called letters, each of these A's. The set of letters, they sit in some finite set of letters, A1 up to AN, say, or A, let me say, even whatever, AD, since n was the number of particles. There's D of them. This is called the alphabet. And I simply just define the class of functions recursively this way, declaring that weight 0 functions are constants, weight 1 functions are logarithms, weight 2 functions are things that differentiate to logarithms with a certain specified set of possible arguments. I've declared ahead of time what they're going to be. Okay, and there's a nice tool to represent such functions called the symbol. And that can be defined recursively just following this equation. Take the derivative, record which k minus 1 functions here in each of the coefficients, and then define the symbol recursively by just stripping off the argument of that last d logarithm and recording it. Okay, so if I do this and I go recursively, what will happen? I'll go all the way down until I get to weight 1, and then that's the last one, that's the last log, and then I'm done. So you end up with a sum over k tuples in the k-fold tensor product of the space of letters. Okay, and there are some coefficients, one for each possible k tuple. And these coefficients are not arbitrary. They satisfy some constraints. In particular, they satisfy the fact that if I take d squared f of k, this had better be identically 0. So applying that here, I'm going to get some constraints that relate to different coefficients. And not only does it apply to the weight k, it also applies to the weight k minus 1 coefficients. So all the way down, these coefficients satisfy, they talk to each other such that this condition is satisfied. So there has to be some consistency condition amongst these coefficients in order for this to be true. Right, so now, having specified a class of functions, to actually tell you which class of functions, I have to tell you what is the alphabet. And then this does the definition. Okay, so it was observed by, in a paper 2013, that of the functions that are relevant here, for low loop orders, in that case it was L equals 2. For, I think, arbitrary multiplicity, at least for the MHV case, it was observed that in the answers, they were of this form, and the letters in the alphabet all corresponded to cluster variables associated to the Grassmannian cluster algebra GR4n. Okay, so observation. This was Golden, Goncharov, Spradlin, Vergu, Volovich, 2013. L equals 2 results consistent with alphabet contained in the set of cluster variables. For GR4n, which is our space, the GR4n cluster algebra. Okay, and I introduced that in the last lecture. I drew for you an initial quiver diagram. We put certain Plücke variables from GR4n at each of the nodes. There were lots of arrows. And then we talked about how you do mutations in the cluster algebra to generate new variables, which are rational functions of the starting ones. Okay, and in fact, I said rational functions, but in this case, the Plücke relations and the Laurent phenomenon in cluster algebras always simplifies each result such that at every node you find a polynomial in the Plücke variables. Okay. Right, so you get these are Plücke variables, A, B, C, D, and polynomials in them. Certain polynomials. Right, so that's nice. Cluster algebras seem to be telling you something about the class of functions that are relevant, at least at low multiplicity and at least at low loop order. That's already useful, because if you know that, you can make an ansatz in this space of functions and then go and look for a function in there that has the properties to be a scattering amplitude. Okay, so when some two loop results were known, it became possible with this observation just to make an ansatz for 3 loop amplitudes. You have a finite set of possible functions that you can generate this way, and then you can look at them and say which of these have the good branch cuts, which of these have the correct properties that come from supersymmetry of the underlying theory, for example, and the correct properties in the collinear limit to behave like a scattering amplitude in a quantum field theory. And you can start to isolate the correct answer, or at least an answer within this small ansatz which is consistent with these properties. And then you can try and convince yourself that it satisfies very many other self-consistency conditions. And if you manage to do this, you declare victory and say, aha, that must be the actual answer for the scattering amplitude.
Also worthwhile adding that
Thank you. I should have mentioned that. So yes, the work that you are referring to made use of this technology that existed in the mathematics literature, and in particular was certainly known to Goncharov at the time, and Spradlin, Volovich, and Vergu, together with Goncharov, successfully used this to turn the L equals 2, N equals 6 MHV amplitude from something monstrous that was computed directly from the Wilson loop calculation into a very manageable few lines expression, explicitly written in terms of quadrilogarithms. Thanks, David. Okay, so something came about through this, and then later was noticed, based on the new results that could be produced by using this knowledge, that there's an additional property. So this was work with my student and Omar Gurdwan in Southampton. There's an additional property where you find that neighboring letters are correlated with each other. So remember, we can represent some information about our function just by thinking about these k-tuples, these coefficients. The neighboring letters in each term. So you have something, then you have a letter A, then you have a letter B, and then you have a bunch of other things. It turns out that you don't have all possible A's and B's in your alphabet. So A and B are only possible, by which I mean they can come with a non-zero coefficient if they appear together in some seed or some cluster of the cluster algebra. Okay, so that's quite a surprising property. Part of it is not so surprising because it actually relates, a subset of these conditions are related to the Steinman conditions, which say something about consecutive branch cuts when of a particular type. So some subset of these letters on the first Riemann sheet, you take a discontinuity in them. You can then not take a discontinuity around a crossing cut. Okay, so let me not draw it, but there's a subset of these conditions that are related to something that's known since long before. Okay. So some consequences of this. So let me just say, imagine we are in this situation. So if I take an antisymmetric pairing here, if I take a given coefficient and I anti-symmetrize, so I fix this bit on the left, I fix this bit on the right, and I just look at all the terms that have something here and something here, and then I anti-symmetrize that object. That thing is subject to these integrability conditions. So those quantities are constrained by that property that d squared f must vanish. Those coefficients must satisfy some relations. But when they do, then this cluster adjacency property seems to be automatic. The integrability for these combinations implies the adjacency. That's for these. But you can also take the symmetric combination. And these trivially obey the integrability condition, so integrability imposes no such constraints. But adjacency says that B and A should still appear in the same seed. So this is where it's doing its work. Right? It's somehow it's orthogonal to the conditions of integrability. It takes the piece that's trivially integrable and says, no, that's got to be constrained also. Okay, and there's another property that's interesting, also has a cluster algebraic structure. I can consider triples. So now what I can do is I can just compute all possible weight-free words in this alphabet that obey the integrability conditions and obey the adjacency conditions. Fix your alphabet, compute all possible weight 3 words that are integrable. Integrable, I mean d squared f equals 0. And you find the triples are of 2 forms. You can have A tensor B tensor C, where A, B, and C are all found in the same cluster, same seed. Or you can have A tensor something tensor A prime, where A prime is not in the same seed as A, and therefore it could not appear next to A by the adjacency constraint. But not only that, it must be a mutation partner of A. So remember we had this operation of mutation. I have a cluster variable on a node. If I mutate on that node, I will obtain another variable. By just changing that variable in that seed, I get the next seed along in the mutation, and I have a new variable there. That variable is always incompatible with the variable I started off with. There's no seed that contains both of these. Okay, so A and A prime are a mutation pair. And the thing in the middle, I called it Z. It has to be the edge variable, Z. Let me say Z, A prime. It's the edge variable. Associated to this mutation. And you'll remember the edge variables, we introduced those. There's one for each mutation, and in that mutation, the variable on that node inverts, and then all the others change in some way. Okay, so the edge variables associated to edges that connect 2 different seeds by a mutation, and whereas the cluster variables are such that it's one particular cluster variable which changes on a mutation. And this combination is exactly the kind of thing that you see when you find 2 incompatible cluster variables separated by 1 step. Okay. So I drew this picture yesterday. In the case n equals 6, you find that the GR46 cluster algebra is of A3 type, and it has the underlying mutation structure given by the 14 corners corresponding to seeds in this diagram, each edge corresponding to a mutation between corners. And then each face corresponds to a cluster variable. So if I start here in some seed, and I mutate away from this face, I go along this edge up to this corner, which is this seed. And then this corner retains 2 of the faces that were shared by this initial seed, but it loses the one that I mutated, and it gains its mutation partner, which is here. Good. So there are 15 Pluker variables in GR46. It's 6 choose 4. But I should have homogeneous multiplicative combinations of those, and there are 6 scalings. So there are 9 independent multiplicative combinations. And that is also the same as the number of faces on this diagram. Okay, so however, the faces on this diagram, what they do is they label the active nodes in the cluster, and the frozen variables are not depicted on this diagram. Okay, so there are also 9 active cluster variables and 6 frozen variables, which makes 15, as we just counted, and there are 9 homogeneous combinations of those. Okay. All right, so, okay, I even got an example. So like this face, for example, I could label by 1, 2, 3, 5. It's a minor. This face here, label by 1, 2, 4, 6. And this edge, or this edge, actually, which takes us between these two faces. It's the same variable for each edge, because it connects the same two faces. It would be this homogeneous ratio, 1, 2, 3, 4, 1, 2, 5, 6, over 1, 2, 3, 6, 5. That's the Z that sits on that edge. Okay, so then in the symbol, you could have this thing, then this combination, and then this thing. And you're worrying about why I'm writing some non-homogeneous things and some homogeneous things. Remember, they're all arguments of d logs, so I can expand them all out. Multiplicatively, I can just make linear combinations of d logs. I have products or ratios of these variables. Right, how much time have I got? Right, I really want to talk about how the square roots show up. So, nearly. Okay, so there's a problem, an obvious problem. We talked about various cluster algebras, and we said that sometimes you mutate and mutate and you get back to where you started, and then that's everything that you can cover. More likely, when you've got a sufficiently many nodes and arrows, you start mutating and you just carry on going forever. And the thing does not close into some closed shape, some nice closed shape like this one. This is a very special case. And the first case that happens for GR4n is GR48. Okay, so this was GR46. It's A3 type. Cluster algebra. GR47 is also finite. It's an E6 type, some generalized six-dimensional associahedron that I can't draw. And then GR48 is nine-dimensional, and it is not finite. So that's potentially a problem. Where's your alphabet? They've got infinitely many things to write down. That's not good. And to sum up, particular loop order, even if the thing remains polylogarithmic, and even if they were all in that alphabet, a given finite loop order amplitude can obviously only have finitely many singularities. So, which ones? There's another problem. So, known amplitudes at 8 points, even starting at one loop, n equals 8, have polylogarithmic functions whose letters are algebraic functions containing square roots of the basic data. So, have quantities that look like a plus b root delta over a minus b root delta. And I'm writing it this way because obviously the product would rationalize. So AB and delta are all polynomials here. In minors, the product would rationalize, so I won't call that algebraic, but I can also have the ratio, which doesn't rationalize, and that does appear in expressions for amplitude. I have to be able to understand how such things can appear. Does this just mean that you can't apply this cluster algebra technology beyond n equals 7? Okay, so all right. Absolutely, yeah. So, I mean, already the good old one loop 4 mass box, when you write it in terms of these data, is of this form. Oh, this is obviously problematic. So what we need is a way of truncating the alphabet to some finite set and a way of generating some algebraic letters. And obviously I'm connecting this discussion to the discussion of the preceding 2 lectures. So it's going to be related to certain infinite sequences of things that you can do in the cluster algebra. Now I had an aside here. Maybe I can say something. Okay, let me try, and then we'll see how we do. So, hint at how to proceed is to have a look at the tropical version of the Grassmannian. Okay, and so this was something that was studied by and Sturmfels. 4. You can look at a tropical version of the Grassmannian space, which retains lots of this information about its combinatorics, okay, but then greatly simplifies the nature of the space. So what does that mean? So take the ideal generated by all the Plücker relations. So, for example, now I'll just do a very toy example, GR24 has six minors and 1 relation. Looks like this. This is the Plücker relation for GR24. And then you say, well, on the left-hand side, I've got this polynomial. So let's tropicalize this polynomial. So to tropicalize, we study not this polynomial, but rather a convention, let's say the minimum of P12. So here's a product. So I've got 3 terms. So I'm going to have 3 arguments in my minimum, and a product becomes the sum. So P12 plus P34, P13 plus P24, P14 plus P23. Look at this object. It lives in some 6-dimensional space spanned by these 6 variables, and it chops it up into regions of piecewise linearity, right? Because I have a minimum function, so it's not the same function everywhere in the space. It's linear, but therefore it's linear by region. Okay. So what do? So we study this 6-dimensional space, and we study these regions of linearity. I'm saying it's 6-dimensional, but there's clearly an invariance here, a 4-dimensional invariance. If I study this vector, P12 all the way down to P34, and I shift it, so if this gets shifted by the following shift, where Pij maps to Pij plus Ai plus Aj, so I have 4 possible shift variables, Ai, then this relation's just left invariant. I'm not changing any of the regions if I do such a shift. So 4 of these 6 dimensions don't really matter, and I can collapse the thing down to 2 dimensions remaining by modding out by this shift to study the different regions of piecewise linearity of this one function. Okay, so what does it look like? So I have to study this thing, and what I'm going to look for now, if I want to study the junctions between the different regions of piecewise linearity, what has to happen is that I have to find places where one argument is equal to another argument, and they're both the minimum. Right? Because that's the place where that's changing between this one being the minimum and this one being the minimum. Okay, so how do we do that? So we've got three possible ways of doing this. We could have three ways to find tropical hypersurface. This means these junctions between the regions. We could have P12 plus P34 equals P13 plus P24, both less than or equal to P14 plus P23. Or you could have P12 plus P34 equals P14 plus P23. I exchange the role of these two. Or finally, the last one. Okay. And now the job is just to characterize where in this space are the rays which join between these regions. Okay, and I've argued that we can project the whole thing down to 2 dimensions. So let me draw it in 2 dimensions. And then you find 3 rays, each defined by each of these 3 conditions, which we could characterize by, for example, this one. So it's here, P14, let's say, equals to 1, rest equal to 0. Just go in the P14 direction. That satisfies this. Or here, P13 equals 1, 0. Or here, P12 equals 1, the rest equals 0. And then when I mod out by this 4-dimensional shift, I can project those down to a 2-dimensional plane, and I have these 3 rays, P12, P13, P14. Okay, very simple. So there are 3 regions. There's also a notion of the positive part. So here we just did the Grassmannian. The cluster algebra is connected to the positive part of the Grassmannian because it preserves a positivity structure. The positive part is you can recover by looking at the signs of the terms that you turned on in the original Plücke relation, and then you pick the 2 that have opposite signs. So the only one that doesn't work is if I pick this one and this one. That's not a positive ray. So 1,4 and 1,2, that was this one, this middle one. This is not positive, this one's positive, and this one's positive. So this is the positive part. And by the positive combination of these rays. Yes. And there are other ways. There are other ways to get just the positive part, but this is a way to recover it from the full tropical fan once you've done the work of, not much work in this case, of constructing the full tropical fan. Okay, so now the length of these things really don't matter. So I could just intersect this with the unit circle, and then really my space is just 3 isolated points, 2 of which are in the positive part, and 1 which is somewhere else. These are the positive bits. Right, now I'm just going to draw the answer for the next case for GR25. And then hopefully, and doubtfully, looking at the clock, say what happens for GR48. So let me draw the analog of that 3 rays intersected with the circle for GR25. Just as the next case, if you haven't seen this, it's a good exercise to figure it down. So all you had to do here in this instance is write down all 5 Plücker relations, work out where you are in the junctions of something that's swapping between the different regions of piecewise linearity, cut out by all 5 of them. Okay, and I'll leave that as an exercise. You find there are 10 interesting rays cut out by this space. And also in this instance, you find solutions that are positive linear combinations of 2 different rays. In that case, there were just 3 isolated rays. In this case, we have 10 rays and edges between certain pairs. And this is the combinatorics of those rays and their connections. The red bit in the middle is the positive part. So that's an exercise to recover this, which, if somebody is interested, we can go through maybe tomorrow. Right, so this is related, this positive part. So once you've got these rays, you can recover the G-vector fan of the underlying cluster algebra. So you can relate the positive part to the G-vector fan. And you remember we drew the G-vector fan for a case at A2 type, which GR525 is. So we can connect this picture to the cluster algebra. The way to do it is to take the edge variables in your initial seed, I called them Z1 and Z2. So let me write them in terms of Plücker variables. You just get this from the quiver diagram. Then you tropicalize. I called the tropical versions of Z1 V1. So that will just be P12 plus P34 minus P23 minus P14. And V2, the same thing, P13 plus P45 minus P34 minus P15. Just tropicalizing those simple monomials. And then I evaluate these right-hand sides on the rays that you find here. In this instance, for example, this ray points in the direction P12, this one in the direction P34. So P12 will map to the vector 1, 0. So this ray, the ray P12, becomes this ray, which was indeed one of the G vectors of our initial seed. If I take the other 5, I will recover all the other 5 G vectors, the other 4 G vectors that you generate by mutations from the cluster algebra. And I think, strictly speaking, because I took the minimum there, I actually generate the G vectors in the opposite cluster algebra. But okay, that's a choice of convention of how you tropicalize. Okay, so we get the G vector fan, right? This thing gives us, this is the G vector fan, or the GR25 cluster algebra. Right, so that's good, because now I can do the same trick to GR48, imagining I'm powerful enough to compute the tropical, all the tropical hypersurfaces that you would get in GR48. I'm not going to do that, but I'm going to just point out something interesting that happens. So you will get always, because I've got finitely many equations that specify, strictly speaking, I guess I should take a Grosvenor basis for the ideal, but there's always finitely many polynomials that will specify a Grosvenor basis for the ideal. You tropicalize, you find finitely many rays with some connectivity structure. never infinitely many rays. Okay, so if you do that for GR48, you find finitely many G vectors. So a subset of G vectors that come from the rays of the tropical fan. Tropical positive part of the Grassmannian. But you don't only find G vectors, you also find some other rays. In this case, just a handful, 4. 2 of those rays, so 2 of these, are the things that we called, in this language of converting the tropical Grassmannian to the G vector fan of the cluster algebra, 2 of them are what we called G1 infinity, which was the fixed point of our first braid generator. So this you get by sticking in a random vector, and you iterate sigma 1 very, very many times, and then you find you're pointing in a certain direction. And then that must be a fixed point of this vector. It's also invariant under sigma 3. We had four braid generators in this case, related to each other by some cyclic structure. You get the second one, that was the fixed point of G2 of sigma 2 and sigma 4. And you get 2 others, for example, G3. This one you can recover by applying sigma 2 to G1. So you get something that you can generate by the action of the automorphism group. And you get G4, which is the action of sigma 1 on G2. Okay, so there's some interesting stuff. It's telling you, A, it's finite, good. B, extra stuff. Okay, and now we know something about that extra stuff because we know it's related to the application. Time is almost over, and so let me write, basically, I'm going to draw one picture, and then I'm going to write maybe 2 formulas. Okay. Maybe 3 formulas. Okay. So, what you can do is you can go and look. We know these things come about through some infinite mutation sequence because we can obtain them by this infinite iteration of the automorphisms, and automorphisms are just an encoding of certain mutation sequences that preserve the shape of the quiver diagram in the seed. So there are certain infinite sequences of mutations that will take us off in this direction, and it's possible to identify certain seeds with certain quiver diagrams that do a nice job for doing that. And they take this form. They have a double arrow, an entry 2 in the exchange matrix, 2 arrows going between the same pair of nodes, and then simple arrows on the other nodes that look something like this, and there's some tails. Okay, and there should be 9 nodes in total. So you find diagrams, there are certain seeds that have this structure, and then the infinite directions that you can move off in that correspond to going off into these limiting directions, when you find such a seed, you can mutate here or mutate here in alternating directions. Just keep oscillating between this. It preserves the shape of this quiver diagram. And again, it's important that these arrows point this way for that to happen. They do. So there's a certain natural set of seeds and certain natural infinite sequences, and you can find the ones that go off in these directions that go to the these limiting rays that correspond to the limits of these automorphisms. Okay. So if I put some labels, okay, so I've got different labels, but let me call these cluster variable B1, B2, it's this one, B3, this one's Z0, this one's W0, and the rest I'm not going to bother about. Imagine, just take those as labels for cluster variables on those nodes. They stand for certain polynomials in the Plucker variables. Okay, and then you compute the mutations, and you find that, there were some frozen variables which I did not draw in this picture, but one should take them into account also when doing this mutation relation. You find that these things generate an infinite sequence. Suppose I mutate at W0, I'll get something that I'll call Z1. Then I'll mutate at Z1 and obtain something that I'll call Z2. And I just keep going and I get an infinite sequences of Zs. And you get a recursion relation that just follows from the mutations of how to compute these things. Has some basic structure. Let's put this object here, there, something like this, where C is the product of the B's times a frozen variable that I didn't write in the picture, and this F is also a product of some frozen variables that I didn't write in the picture, but the relevant ones are the ones that connect to these nodes with the double arrow. So collect all the frozen variables that come into these two nodes, call them Fz and Fw, and then this is a formula for the recursion that you get for this infinite sequence. No, that's just completely standard from the cluster algebra. However, there's a linear version. So there's something interesting happens. So this sequence you can write in the following form. Let me make a matrix of these variables. This follows just by following the mutation rule. Right? And the fact that it's quadratic is that there's a double arrow here. That's where that power comes from. Yeah. Let me make this symmetric matrix of this sequence of variables. I can rewrite this thing as a matrix recursion. If I find some matrix of the form P1 minus F0, that I act on the right, and this is true for each Zn, so I can just iterate this all the way down, and I can take this all the way down to Z2, Z1, Z1, Z0, this matrix, P1 minus F0 to the nth power. Okay, and if I take the determinant of this relation, I just get back this relation that I already had. But if you are able to find a P such that this works, you can recover a linear recursion relation. So you find a linear relation. So to be consistent, you need Z2 equals Z1P minus Z0F. Okay? Just by the fact that I've got all the same variables appearing here, and this has to hold. So for that to hold, you can write an equation for P. Z1, Z1 plus FZ W0. So you can create a formula for P which is built from data. Excuse me, there's also Z0, Z1 factor here. So I can cancel the Z1s in this formula, this consistency relation to hold. But all the data here is just sitting here in this picture. And then for this to hold, it has to be true. You can argue by taking the square of this that actually there's a factor of Z0 on the right-hand side, albeit it's not apparent. Okay, so it must be that when I write these things out and I make use of the Plücke relations, you can find a factor of Z0. The way you argue this is by taking the square, using mutation relations to pull out a factor of Z0. You find it has to vanish at Z0. If the square vanishes at Z0, so must the original object. And therefore, I can divide by this factor on the left, and what's on the right must be a polynomial. So there's some special polynomial that's associated to this recursion relation. Okay, and then that gives us, finally, this algebraic letter. So this recurrence becomes linear. Zn plus 2 is equal to Zn plus 1 P minus Znf. You just have a linear recurrence that's manifestly polynomial. Okay, and if these factors were 1, this would be Fibonacci, and I would write down the golden ratio as the sort of the limiting asymptotic behavior of the series. And you can just do the same thing, but now the golden ratio becomes a function of P and F. So now it's a function of the polynomials. And then, okay, so then let me just write it here since I'm right at the end. Here is the final formula. There's some factor, it's irrelevant. And then we have Z0 plus, some quantity that you can compute from that data, the square root of delta, P plus root delta to the n, plus Z0 minus B root delta, P minus root delta to the n, as an explicit solution, algebraic solution of the recurrence relation, just like you do with the Fibonacci numbers and the golden ratio. So then this, over this, gives us the algebraic letter. So you can find these algebraic letters in certain infinite mutation sequences. So you look for all of these. You can recover all the different mutation sequences that go to a particular direction, say this one. They all have the same delta, but they have different Z0s and Bs. So you collect a set of algebraic letters by finding these sequences. They turn out not to be all multiplicatively independent, but the ones that you do find, in this instance, you find 9 for each G. So you find 9 for this guy and 9 for this guy. And those 18 are precisely the set of 18 algebraic letters that appear in a 2-loop NMHV octagon 8-point amplitude calculation of Songhe and collaborators from a few years ago, 2019, I think. So there is a way to recover the algebraic letters. And also, it turns out that the rational letters in that expression are all contained. They are related to the G vectors in this finite fan that you get by tropicalizing the Grassmannian. They're a subset. So you certainly don't exhaust all the ones in there, but they're a subset. Okay, so there are many open questions, but I'm well over time, so ask afterwards.